So hello everyone, my name is Adam Jones and I'm currently studying a PhD with the University of South Wales and TATA Steel packaging. So a little background, if you can see the top left-hand image on the slide, this is a picture taken at TATA Steel of the electrolytic chromium coated steel product travelling through the production line. If we follow the green arrow downwards, we can see the layer structure of this product. So it has a steel substrate of less than 0.5 millimeter thick, a metallic chromium layer and a chromium oxide layer of less than 50 nanometers thick, and it has an oil layer on top for further lubrication. So following this arrow right, this type of steel is used for packaging products, so such as food and drinks cans, and without this chrome coating, the steel may rust from being exposed to air or dissolved from its corrosive contents. So the problem that TATA is facing with this ECCS product is a production line measurement systems result for the chrome thicknesses are not accurate to their offline measurement systems. So TATA wants to optimize their production line systems to ensure that their customers are always satisfied. But now they're having to slow down the production line, use increased electrical current and more chromate acid solution for the electroplating process, which is resulting in business costs greater than £3,000 per week, let alone the research costs resulting from many attempts to optimize these systems over the past 2 decades. So this leads to my research question, which is develop a new chrome thickness measurement system that can measure nanometer scale chrome thickness without contact, non-destructively, in real time. So this led to a literature review that aimed to identify potential novel methods that could be applied to this application. And 3 methods were found, all optical in nature, which had high potential based off similar application areas, such as the automotive industry and the semiconductor industry. And these optical methods are based off light reflection from the product surface and measuring optical parameters that could be modeled to evaluate this coating thickness. So to prove these optical concepts further, theoretical and numerical simulations were conducted, which yielded very positive results in the thickness ranges defined. Experimental design and procurement was then completed to conduct experimental trials on these optical methodologies. So now I'm at the experimental stage, where I'm continuing to develop experiments to prove that these reflection methodologies will apply to this particular application. So I've had some very interesting positive results, and I'm currently continuing to validate the potential of a method called spectral reflectometry. So the process of this method is to store reflection models of the samples I've been given with known coating thickness values. When live measurement is taken using a self-created software application, these spectral profiles will then be regressed against the stored model using statistical analysis to evaluate this coating thickness.